if we're in the time domain and we want to know some facts about what's going on, if we're in the Laplace domain, we want to know what's going on in the time domain, we have two theorems that are going to be useful. So today we're going to talk about what these theorems are, when we can use them, and after I describe that, then I'll also go into the proofs in case you want the evidence as to how it comes from. So, the final value theorem says that if we have a system in the Laplace domain, a function in the Laplace domain, and we multiply that function by s, and see that all real parts of the poles of s times the function of s are all less than 0, that means that we can predict the final value by taking the limit as s goes to 0 of s times phi of s, and that would be equal to the limit as time goes to infinity of that same function in the time domain. The initial value theorem is going to tell us that if we take some function, and here we don't have any sort of restriction about if what the real parts of the poles are, but we take some function and we take the limit s as s goes to infinity of s times phi of s, that's going to be equal to the limit as time goes to 0 of phi of t. So final value theorem lets us take the limit as s equals to 0 of s times a function in the Laplace domain to find out what's the final value of this theorem. And the initial value of the theorem is going to say that if we have any function and we want to know what the starting value was, we could do that by taking the limit as s goes to infinity. So that's going to be nice and useful to figure out where things are. And the reason we need to have all real parts of the poles going to that of s times phi of s is less than 0 is that's going to be a system that has an equilibrium. So when we talk about stability, we'll get to that in the future, but if you had a sine function or a cosine function or a function that goes to positive or negative infinity, then the final value theorem does not work. So we always need to check for that. But here's our proof. So Laplace transform, we can say the Laplace transform of derivative is s times the function of s minus initial condition. We also have it defined by that integral as 0 to infinity e to the negative st times a function dt. And we can combine these two to say that we have s times phi of s minus our initial value. So that's the Laplace transform of the first derivative of a function written one way. It's also equal to the integral, which is that same result, just writing in a different format. Now, if we take the limit as s goes to 0 of these two equations, then what we're going to see is that the limit as s goes to 0 of the first half, we'll just keep that and not change it at all, but that's going to be equal to the integral of 0 to infinity of e to the negative 0t times the derivative of our function dt. Now that e to the negative 0, doesn't matter if it's negative or positive, e to the 0 is 0. E to the power of 0 is 1. Of anything to the power of 0 is 1. So we're going to, let's also fix that parentheses. We're going to be able to say that the integral of the derivative function is the original function. So we can say the limit as s goes to 0 of s times phi of s is equal to phi of infinity in the time domain. We're going to use a similar method to find, so that proves the final value theorem, and we're going to use a similar method in order to prove the initial value theorem. And so we'll again take that original Laplace transform of derivative in both formats that we've seen it, either using the integral or just s phi of s minus phi initial. And if we take the limit as s goes to infinity, that e to the negative st term will go to 0, which means we can say the limit of s goes to infinity minus phi initial is equal to 0, or the limit as s goes to infinity, s phi of s is equal to the initial condition. So that's the proof of both.